So our next speaker, you guys saw him yesterday participating on a panel discussion. He's the VP of Technology at, it's a little website, oh yeah, Facebook. And he's going to be talking about the social graph and what it means and why it's so important and what the database has to do with it. So please give a big round for Jeff Rothschild.
Good morning. You know, it's a beautiful morning, just like today, last summer. At the end of the summer, I was sitting at my desk, and I was thinking that whatever important thing I was working on probably would still be important a few days later. So I called my wife and said, let's get up to Tahoe for a few days. She got busy packing the car, and when I got home from work, we headed up to the mountains. But little did I know that night, when I was unpacking the car and bringing the cooler into the house, that the house was being staked out and I was being observed. Because no more than a half an hour after turning out the lights, I woke up to this thundering noise from downstairs, and it sounded like somebody was remodeling our kitchen. And as hard as I tried to, block this out of my mind and get back to sleep, eventually I knew I had to face the fact that there was a bear in the kitchen, and I was going to have to deal with it. Well, my dog which is a golden retriever, was growling like a pit bull, so I knew he shouldn't be part of this. So I locked him up, headed down the stairs, screamed at the bear going down, because the last thing you want to do is meet that bear in the kitchen. And the last thing I saw was the bear hightailing it out of the porch door. Well, he did leave in a hurry, because as he was leaving, he managed to drop about a 2-pound block of cheddar cheese. But he did make off with a package of fresh tortillas. And as I was cleaning up the kitchen for the next hour and a half, at least I had the satisfaction of knowing that neither one of us were going to have quesadillas the next day. Now, you might ask, why would I tell you the story? It really is because the following morning when I got up, I did what anyone would do. You write a blog post, you write a note, and I put a note which would appear on my Facebook profile. And what was so fascinating was that within 3 minutes of posting this note, people were commenting on it. And then people were commenting on the comments. And then a discussion ensued, like, well, what actually was Jeff saying to that bear? Was he giving him a hard time about test plans? And it wasn't true at all. I was suggesting an exit strategy. But what this really proved, and what it really brought home to me, was the power of the social graph to accelerate the speed at which information can flow through the network. And today we're going to take a look at the social graph and what it means for the database. So, what is this thing we call the graph? Well, at its heart, it's people and the connections between them. And the graph itself is an interesting application in its own right, and we've all spent time browsing through people to whom we're connected, communicating with them, and just learning about people who are within your world. But as we saw from the example of the blog post about the bear, it can be much more than that. It can be a powerful tool for accelerating the use of an application. And by example, I'd like to pick on Facebook Photos, because at its heart, this doesn't look that different from any other photo application that you've probably seen a dozen times online for the last 10 or 12 years. It's a collection of thumbnails that can be viewed as a group, or that you can view for higher resolution. You can sequentially click through them. However, when you add photo tagging to the application, so you can identify specific individuals, and when this tagging is supported by a foundation of the social graph, interesting things happen, such as getting an email. And if that email has a note in there telling you that a picture of you is available online, it's really tough to resist. I can't resist it, and I always will click through it. I'm not sure if it's because of curiosity, or whether it's fear, or it's a combination of both. But when I find that there's new content about me online, whether it's a photo, a video, I mentioned in somebody's note, I'm always going to take a look. And in this way, it's clear that the social graph has transformed a seemingly simple application such as photos into something which is tremendously more powerful. And it's not only myself who's going to want to take a look at this, it's also my friends. Now, they may not be interested enough to get an email notice saying that, clogging up their inbox saying that a picture of me is online, but if they get a news feed story saying that 10 or 12 of their friends have been tagged recently in photos, it's highly likely they're going to want to browse through that and take a look at those pictures and see what their friends have been up to. So the social graph underlying photos creates a fundamentally different application. It's a transformative technology. And I'd like to say that when we launched photos on Facebook, that we really understood how this was going to drive usage, and that we had anticipated this, had enough storage, and we had enough servers available to adequately handle that load. And probably in about 10 years, that's exactly how I'll remember it. But the truth is that we blew through the first 6 months of storage in about 6 weeks, and today users have uploaded to Facebook over 6.5 billion photos. We store those in 4 resolutions for easy viewing, resulting in 26 billion photos in the archive. But even more interesting and more impressive than the growth in the content was actually the growth in the usage, because underlying this was the social graph, and the social graph drove people to look at these photos. So today, we're serving over 250,000 photos every second at our peak load. And that doesn't include the profile content of the site, which is another 200,000 images. So Facebook today is one of the largest, or it actually serves more images than any of the other photo sites. And it's because of the way the graph has driven the usage of the application. So another application that is a good example of how the social graph, good example of the power of the social graph, is email invitations. We've all seen emails that invite us to an event, and sometimes we click through on them, and sometimes we don't. But if you get a news feed story telling you that 12 of your friends are going to be attending an event, it's an entirely different experience. And this isn't an invitation. This is simply information that your friends are, and possibly your friends, certainly people with whom you have a relationship, are attending. And maybe it's enough information to know that you're going to want to go. Perhaps it's enough information to know that you're not going to want to go. But it's highly likely that you're going to click on this, or if you happen to receive an invitation, you click on that, and it takes you to a very dynamic page, a page that shows you who's attending, who isn't attending, information about the event, and the ability to have a dialogue with other attendees or potentially the host of the event. And it's not surprising that today Facebook is serving more event invitations than any website that's dedicated to that purpose. So after launching these applications, it became clear to us about the power of the social graph and how it could really turbocharge an application. But the question facing us, well, what's the best way to use this? Was it to build as many applications as we could and take advantage of the unfair advantage that the graph would offer to these applications? I mean, that would have been an entirely acceptable response, but it isn't the path we took. What we did instead, after we got, was to, do what I tell you? Okay. Was we recognized that in no way did we have a lock on all the interesting ideas. And we couldn't even come close to believing that we were going to have all the creative ideas of how to use this graph to our users' benefit. And even if we did, what's the chance that we could implement them? So instead of getting to work building applications, we instead got to work building a platform and an API so that other developers could launch applications on the graph, both within Facebook and on their own sites. And in May of 2007, we introduced the Facebook platform. And today, there's over 20,000 applications that have been developed for platform. Many of these applications have been wonderfully successful, but this is still a ground floor opportunity. And it's almost without question that we haven't yet seen the most valuable and interesting applications that will be developed on top of the social graph. And while we're likely to be surprised by the nature of the next killer application, almost certainly we're going to see valuable applications in the area of sports, education, healthcare, and business, areas that to date have been somewhat underserved. So, introducing an application into a pre-populated user graph with 70 million active users is a little bit like standing next to a railroad track and throwing a grappling hook onto a passing freight train. I mean, the acceleration is exhilarating. Unfortunately, it can also be a little bit painful. And at the risk of picking on one of our early successful developers, iLike, if you ever have a chance to meet a member of the iLike team, ask them about the exhilaration of adding 20,000 users an hour. But today, we have over 200 applications that have over 1 million users, which clearly represents that Facebook platform is a tremendous opportunity to a wide array of developers in order to where they can create new value and new utility for users by building on the power of the social graph. So, if the graph is good, you would think that a richer graph is better, and it is. A richer graph offers more utility, and if the graph offers more utility, then it offers more utility to more users, and more information is going to flow through the graph. So what we have is a virtuous circle with positive feedback, all of which we think moves things in the right direction and brings people closer together and improves the flow of information between individuals and helps improve communications within social circles. However, people are only one dimension of this graph. The graph and the social applications also connect people to things, to photos, videos, groups, organizations, events, even other applications. And when we pull all of this data together, it looks something like this. What we see is a lot of different types of data, a lot of connections between people across many networks, a lot of media, and a lot of work for our database. So the remainder of this presentation, we're going to take a look at the impact and challenges on the database for supporting a rich social application at scale. So let's look at the data. We'll start with an individual. And from that individual, we have connections to other people. And each of those people have lots of stuff. And if you combine all that together, you recognize that in order to do most of anything that's going to be of interest, and we define interest as integrating information, bringing both people and data together, we're going to be looking at a lot of data. So putting it in simple numerical terms, if you have hundreds of friends and those hundreds of friends each have hundreds of objects, then in order to present your world to you, you could be looking at potentially tens of thousands of objects. Now this should be easy. Databases are good at these things. And actually at one time it was easy. Facebook had its roots as a college website. And each college had its own database. And most users were connected to other users at the same college. So in fact, there was very little that we couldn't do with the right SQL. But our world has changed. Today we have over 70 million active users, and they live in overlapping worlds of work, school, family, and geographic regions. They have connections in their hometowns, they have connections where they live today. And so we simply can no longer represent a cluster of users and their connections inside of a single database. And not surprisingly, instead of partitioning by community, we now partition users fairly randomly across a large number of machines. actually hundreds of MySQL servers. So if we look at what it would take to implement and execute a single page request, well, we can do this in a pretty straightforward way with a parallel query, just running queries across these hundreds of machines at the same time. We collect all the data, do some filtering, and present it to the user. And that would work if we weren't serving a lot of pages. But of course, if we weren't serving a lot of pages, we probably wouldn't have hundreds of database servers. So something else had to be done. Because our goal is to be able to support this operation at massive scale. Today, at our peak loads, we're serving 50,000 user pages a second. So it's useful noting at this point that when most connections are between users and data that are distributed across a large number of servers, that it becomes difficult to use all of the power of the relational model. And for example, joins are very, very rare in our code. However, what is most critical is that we clearly need to limit each page request to touching a small number of databases, or else we're never going to be able to scale this to support that type of a workload. And as many of the people in this room are doing, we use Memcache. Memcache is able to match the access demands of the application and the demand for speed and high access rate, and to bridge that back to our database, which provides us with data integrity, a flexible data model, great replication. And together, it's actually an effective solution, and I think if we can see a show of hands of the number of people who are using Memcache and MySQL together. So, very commonly deployed solution, solves a real-world problem. Our Memcache servers typically serve 50 to 100,000 GET requests per second, something that we're not able to do with the database. And at Facebook, we've done a lot of work on Memcache to improve scalability. We added multi-threading support to better scale with multi-core processors. We've done a lot of work on the Ethernet drivers that run on the Linux boxes, simply because once we had made Memcache multi-threaded, we found that the next bottleneck was simply the single core that was handling all of the interrupt traffic, and we'll be making those changes available to the community as well. And in the pipeline, we have software which is currently baking in our production environment, but we do intend to release to the open source community, and that includes a new C client with improved runtime efficiency, but more importantly, a PHP extension to make this very usable for PHP, UDP support, so that we're able to reduce some of the connection burden seen by the Memcache servers, consistent hashing, so that we're able to modify the configuration of the tier, have it with less disruption on the tier, a new binary protocol for efficiency at both ends of the wire, and slabless allocation to help us avoid some of the problems of slab ghettoization as the workload changes, but the memory allocation between the slabs, memory slabs within Memcache stays static. And probably most importantly, a piece of technology which we call the Memcache proxy. And I had to go into some detail about how we use the proxy in order to scale Facebook beyond a single data center. So 3 years ago, we were located in a single facility in Santa Clara, California. And we had our web tier, our Memcache tier, and our database tier sitting right next to each other. That worked fine until we found that we no longer could expand capacity at that site, and we were going to need to either move to a larger facility or add more capacity. We chose the latter route to add an additional facility. But the problem with adding an additional tier outside the building was we needed to keep the Memcache and the database, and the web tier very close together. I mean, there's a very high rate of requests and a need for that to be maintained at low latency in order to allow the web tier to access Memcache. And doing that even across a regional network didn't feel like it was the right response. We're talking about tens of gigabytes of traffic that exists between the web tier and the Memcache tier. So we built a web tier and a Memcache tier in a new facility in San Francisco. But we continued to use our single MySQL tier because we had managed to limit ourselves to 5 to 10 SQL queries per page. However, the problem arises, how do you maintain coherency between these two caches? The cache in San Francisco will be deleted when a query runs on the San Francisco web tier that updates the cache. And one of the common protocols for managing memcache is that you delete or dirty an item in the cache after updating the database. And the same thing would happen in San Francisco as would happen in Santa Clara. But how do we ensure that the caches between the two facilities were coherent? So we introduced the memcache proxy, and we run all of our dirty traffic, or delete, increment, decrement traffic through the proxy. And in that way, we're able to maintain a coherent cache between these facilities. But eventually, we outgrew the facility in San Francisco. We needed to add a third data center, and we felt that it would be a really good choice to put that on the East Coast. Let the East Coast users enjoy a little bit less network between themselves and our servers here in California. So we used MySQL replication in order to replicate a copy of our database tier to a facility in Virginia, and we implemented a web tier and a corresponding memcache tier in Virginia. But the proxy, used as we were using it on the West Coast, would no longer be a very good fit. The problem we'd be looking at is a potential race condition between the MySQL replication and the memcache replication. Whichever one got there first would determine whether or not we might leave stale data in the cache. And in the cases where the memcache proxy synchronized the East Coast cache first, and the MySQL replication potentially ran a half second behind, then it was easy to see where a subsequent access to data on the East Coast could result in leaving stale data inside the cache. So instead we chose to move the proxy to run on the same server as MySQL, and we extended MySQL to actually call the memcache proxy to do the deletes for us. And today, queries on Facebook look something like this. We've added a memcache dirty clause, which we tag on to the end of every insert or update. And that specifies the keys that need to be dirtied in the cache after that query is applied. And MySQL does that for us. And the important aspect of this is that no matter how many replicas we had, and regardless of the number of regions that those were implemented in, the local cache would be dirtied following the application of the query to the local replica. So we maintain perfect synchronization between memcache and MySQL across a distributed architecture. Another side benefit of this was that it serves to document the relationships between the database and the memcache data, something which generally just exists in the mind of the programmer. So it's great to see that expressed inside of a query. But returning to the question of caching and using caching to optimize performance, the first question you're going to ask is, where do you put the RAM? I mean, if you're looking at potentially millions of requests coming from the application to the cache layer, then you'd better put enough cache at that cache layer in order to prevent those requests from making their way to the database, or else you're going to, of course, swarm the database with too much traffic. And so even if we put enough, and so what we intended to do, what we focused on, was putting enough memory in memcache to give ourselves about a 95% hit rate. But even a 95% hit rate can result in between 500 and 1,000 queries per second going to each and every MySQL server. So you're going to have to put enough memory on the MySQL server to largely hold the working set of requests, or else you're going to overload the disks of those servers. So the answer to the question is, where do you put the cache? It's everywhere. We have caching in memcache, and we have caching in MySQL. And when you factor in the indexes on MySQL, we actually have almost twice as much memory in our database tier as we have in the cache tier. So this is a problem that, of course, we can chip away at through various optimizations. Clearly, we don't want to cache at two levels. It's wasteful of memory, and there's a lot that we're able to do to improve upon this. And in many cases, it's things that people are already doing. So the first optimization is probably only an optimization from the standpoint of maybe your bankers or server vendors, and that's simply buy more hardware. So we're not going to go there. We're going to move beyond that and look at some of the things we can do to actually reduce the memory usage at each level. And the first response is the one that always should be, is tuning. Tuning in the application and in the database. If we think about what causes disk I/O, it's access to pages of memory that actually aren't in memory. So if the queries themselves access fewer pages, then the aggregate of those queries is going to generate fewer I/O requests, and hence we can support more of those queries on a given server, or potentially support and potentially lower the or increase the number of misses that could come from the caching tier to that server, which would then lower the demand for caching and the amount of data that's needed in the caching tier. Or conversely, we can hold the memory constant and increase the amount of data that we put on every database server. So your standard blocking and tackling tuning clearly comes into play in lessening this problem. And another approach is to discriminate between that data which really benefits from double caching and that data which doesn't. There's some data that, when it's pulled through the cache, does little more than simply create turbulence in the cache, displacing other data that has a higher likelihood of being accessed in the future. So that information, you're much better off simply not putting it through the cache, just accessing it from the database. And a case where that occurs very naturally is archive data. It's very common that, and we find, at least within our environment, that we don't cache data coming off the archive systems because the reason we put it on the archive in the first place was it wasn't being accessed very often. So it's a good candidate for information to exclude from the double caching model. But this brings us to our challenge. Clearly, when used together, MySQL and Memcache is a very powerful combination. Memcache is able to match the demands for performance from the application, and MySQL provides us with data integrity, replication, persistence, and a very flexible storage model. But it's also not hard to view this as a problem. Over the last 20 years, CPU speeds have dramatically, and the growth in performance of CPUs has dramatically outstripped the growth in performance of our disk subsystems. And in many and we've given some of the CPU back, but not all of it. And one of the common views is that any growth in CPU is matched by yet another developer framework that trades off runtime efficiency for developer productivity. But the truth is, we haven't given it all back. There's many applications today that simply have to run at the speed of memory, and they've left disk in the dust. And thus, available memory is very frequently the key resource that determines performance or limits scalability. And any architecture that requires that a large portion of our data be cached twice has to be viewed as a problem that's waiting to be solved. So, what does the future hold? What are some of the ways that this problem is likely to be addressed? Well, we've heard about new technology like SQL chips that very possibly will reduce the amount of, through their compression and their ability to support compression at high speed, will reduce the amount of memory that's required at the SQL level to support a given amount of data. And that can reduce then the need for caching. Another technology that holds promise, though, is flash storage. Flash subsystems have the potential for supporting hundreds and thousands of operations per second. However, and that has obviously the potential to greatly improve the scale and performance of the database. But it's not hard to imagine the software that was developed for an environment where we were executing hundreds to potentially 1,000 operations per second may not scale that efficiently into a model where we're doing hundreds of thousands of IOs per second. So this clearly presents both a challenge and an opportunity for the storage engines. And it'll be interesting to see how new emerging storage engines adopt to new storage paradigms, and if they're able to be the key for unlocking the potential of the potential opportunity that these storage systems present to us. However, the database isn't the only place where we could potentially exploit flash storage. I mean, it could be used to address a fundamental limitation of the caching tier, and that is its volatility. Flash is persistent. It has access speeds that are like memory. And we may see things that are a little bit like caches. I hesitate to call them a cache at this point because they become the statement of record for data. But for an application or for data that doesn't really require more flexibility than that offered by a distributed hash table, this in fact may be a very effective solution. And there's other models of structured storage that are emerging on the horizon. And while these are largely untested at scale, though in some cases, the proprietary systems have been run at very high volumes, they offer, again, some interesting potential for restricted use cases. Because as we mentioned earlier, at the point that we partitioned our data, we lost some of the ability to exploit the full relational model. So it's possible that a storage model that strikes a different balance between functionality and performance may be a better fit with some applications. And I don't see these directions as really being entirely independent of each other. I would assume that they're going to be complementary and many will be used within the same application environment. But the one thing that we're confident of is that this bear of a problem, this problem of double occupancy of our data in memory, is going to be solved. The challenge that's ahead of us is whether we're going to see these solutions occur outside the database, or whether we're going to see them through MySQL operating at the speeds of the application. And we're betting on the latter. And we believe that with the strength of the community of developers and users behind MySQL, that it's going to be an important part of the solution. And together, that's our challenge. Thank you.